Hello everyone, welcome to CMST290 where we are almost wrapped up with CMST290. We just finished up learning activity 14 for supervised learning methods where we went through linear regression. We're actually going to jump into the high level of deep learning and understand what is deep learning. And I think the easiest way to do that is through a product called TensorFlow. And let's go ahead and the easiest way to do this is jump out to the internet and then TensorFlow neural network playground, and just do a general search on that. A neural network playground. This is it, TensorFlow. Go ahead and click on this, and you're going to get this nice little setup here, and this is an overview of what a neural network is. You're probably wondering, what is deep learning? Well, this is deep learning. When we talk about deep learning, we're talking about neural networks. And if you want to learn more, go here. There's actually some great technical overview, deep learning by Ian Goodflow, neural networks and deep learning by Michael Nielsen. And there's just a lot of great stuff here. This is actually open source, so you can take this code and reuse it, and you can recreate this. It's a really neat program. And just to kind of give you a heads up of what this is we've got a few things. I won't go through all of this, but high level, what we're doing is this is a over here on the right, this is our target data set. And then over here on our left are patterns or features that we're feeding into it. And in this case, I'm going to do a classification exercise, and I'm going to use a neural network to do that. And we can actually create multiple neural networks. We can create multiple neurons. And I mentioned earlier that these neurons, they operate based on what's called an activation function. In this case, this activation function can be tangent, it can be a sigmoid, it can be a linear, and you can use different mathematically oriented activation functions at each neuron. What that means is these activation functions determine the way these neurons behave. So if I change it to sigmoid, you see what happens. They change into different patterns. And and before I forget, this is called a rectified linear unit, and so that's another different activation function. So linear, sigmoid, tangent, and then rectified linear unit. Okay, and so all of these have different powers, and I will say that the most, the hyperbolic tangent and the rectified linear unit are just a rectifier, which I'll simplify it to a rectifier. These two are probably the most powerful, rectifier and hyperbolic tangents, and you'll see why, because sigmoid and linear, they don't work always in the best cases. They especially when it comes to more complicated patterns. But let's back up here. I'm going to go down to 2 hidden layers. I'm going to keep this real simple. I'm going to do these hidden layers. I'm going to have 2 hidden layers. And when we talk about deep learning, that's what this is actually really referring to, is the neural network and the number of hidden layers within a neural network. And so let me go ahead and get this started. So you see here I've got training data. This is ratio of training to test data, similar to what we were talking about linear regression in our last learning activity. In this case, I'm going to use a tangent for a hyperbolic tangent for our classification problem. And what I'm going to do is I'm going to pass in some 2 features for x1 and x2. And then I'm going to use 3 neurons on the first hidden layer and 2 neurons on the second hidden layer. And these are all going to be bound by the hyperbolic tangent. And what we're going to do is I'm going to push play, and then I'm going to see if this can, and it does it really quick, right? I mean, we get the blue dots, and it finds the blue dots, classifies the blue dots real quickly using the tangent, and finds the orange dots on the outside. So it works great, brilliantly. If we do sigmoid and run the same thing, and we'll see what happens, and doesn't look like anything's happening. It's even when we're going. So sigmoid doesn't work too well. If we go to linear, let's find out. If we do linear, linear is not going to work too well. Why? Because this is a radial pattern. So it's going to kind of sit there and stick and not give us a lot to work with. That's why these are pretty good. This hyperbolic tangent was able to figure it out in no time at all. Now, if I go to this, this pattern is a little bit more complicated. I'm going to run through these again. And looks like the hyperbolic tangent works great, classification. Let's do a sigmoid. Rerun this. Sigmoid doesn't work so well. Let's do a linear, and then we'll see if linear can do anything. And linear is having trouble too determining what's going on. So again, our linear models aren't working out too well. Now, on this one, this is a little interesting because I've got two cluster, like our make blobs example. We got two blobs, and if I do tangent, it's quick. Creates a hyperplane and finds it real quick. If I do a sigmoid, let's see, can a sigmoid work? Sigmoid does great at binary classification here. We got a nice clean line, so sigmoid worked well. And linear should work as well too. See, because I've got a nice split between the two, these other activation functions actually find the pattern real quick, the classification. Now comes the hard one. So I'm going to run through this again. I'm going to do tangent, and then see if tangent can do it. And it looks like tangent's even having trouble here. This is a more complicated pattern because you see I've got these orange lines mixed in with these blue lines, right? In this spiral pattern. So it's trying to figure it out here, and it's starting to kind of do something, you can see here, but it's not quite. And it's having trouble differentiating between everything, and it's taking a lot. See, we're up here at the number of evolutions or epochs. It's sitting here, it's kind of stuck, and it's crossing over. It's not doing a good job of identifying where the blue and the reds are. So I'm going to stop this, and if tangent had trouble, these other two are just not, I mean, sigmoid is not going to work. And then let's see, let's go to linear and then run that one. This is like the others, it's gonna have trouble. It doesn't matter how far along this gets, it's just gonna be stuck. Now, what we can do is we can actually add some more features to see if these help and help it along. So we can provide linear, it's not working. Sigmoid is probably still not going to work because sigmoid is a logistic regression, which is binary, and that's not going to do anything for us. If I do tangent with more features, I might get a little bit more going on, but it's looking a little bit better, but I'm still not quite getting a good classification happening here. I got some orange picking up, but then it's not really strong, the relationships I've got that are being developed. It's trying. See, it's trying really hard to make something happen, but it's not going to work. If I add more features in, let's just activate all these, and then we'll see if tangent can do anything with this. As we give it more, it's actually working a little bit better. You see, I've got a little bit more. It's a little bit more defined. It's getting the blues where the blues are supposed to be. I'm getting some oranges where the oranges are supposed to be, but then I'm still kind of boogered up around these others. I'm not. The background here is I'm not identifying, classifying this properly. So this isn't working. Now, even if the more popular the rectifier. Even if we do a rectifier, let's see what happens here. And this is probably the this is really the definition. This is the mathematical activation, neuron activation of choice. It's the more powerful one, and it's actually doing a much better job already, this algorithm, but it's still having trouble. See, it's still kind of not working out too well. Now, this is the power of neural networks. I can actually add a hidden layer in here, and then I can see if an extra hidden layer helps to classify this problem for us, and we'll see what it does. So it doesn't look like it's doing all that well. Yeah, it's not working out too well for us. But now the other part of my neural art, well, this neural network, not mine, but this neural network for TensorFlow here is I can add stuff on here and get more. I can play around with this real quickly to see if I can't add more power to the neural network and see if we can't resolve this pattern. And that doesn't seem to be working either. So I'm going to throw a couple more neurons at. I'm going to say 6, and I'm going to do 5. I'm going to do 3. So I'm going to do 6, 5, and 3. Let's try that. So we'll run this and see if more neurons actually helps in resolving this and classifying this in better detail. And this is getting close. We might get it with this one. We still have some crossover happening right here, though. See, this is not so, but this is not bad. We got orange where the orange is supposed to be. We got orange right here. We got orange, and then we do have blue, right? And then there's kind of this little bridge that's happening. We got blue over here, but we got this boundary that it's crossing, so it's not a really good. It's getting there, even after we're up at 500 epochs, and it's still not quite. It's going to churn on it. It's going to still try to be. It's going to try to work on this as much as it can, and you can see it's getting there. That's not bad. So 3 hidden layers. We could actually add a bunch more here if we wanted to. We could add more hidden layers and rerun it and see if that helps. This may help. We'll see. I don't know, or it may make it worse. Sometimes adding more doesn't always make it more make it better. In this case, it doesn't. It seems to be making it worse because I've got this whole blue segment now that's out in the orange. So that didn't seem to work. So let's go down. Let's go down to 3 hidden layers. Now, I'm going to leave this on the rectifier for classification, and then there is one thing that we can do here. And remember, there's this concept of training data. So I'm running this algorithm to try to get it to classify, and it's going to try here. It's trying real hard. It's getting there. So one thing I can do is I can actually I can change the ratio by ratio of training data to test data. If I increase the ratio of training to test, in other words, more training data, and see, this isn't bad. This is actually pretty good. I've got the blue, but I've got a little crossover there, a little here, a little touch here, but overall, this didn't do too bad of a job, even after 500 epochs. Okay, so now what I'm going to do is I'm going to increase. Let's go up to 70% and rerun this. And if I give it more training data to work with, will this help resolve our dilemma? So we'll see what it does. So it's thinking on it. It's working it. It's trying really hard. So if it can't figure it out here in about 500 epochs, then it's getting there. It's getting there. So this is actually a pretty good, look at this, is probably one of the best ones we've come across. So I've got a nice clean blue, and I've got a nice spiral, and then I've got classification for orange where there's orange. I got a little bridge here that popped up. but blue where they're supposed to be blue and orange where they're supposed to be orange, and that is a pretty good hit rate. So if I bring this up to 80% and then rerun this, I mean, well, let's see what this does. And I may need to add another neuron to this just to see if that helps. And yeah, so adding extra training data is actually, this is actually helping quite a bit. You can see I've got I have a pretty good delineation here in a short period of time. Within 200 epochs, I've got a nice orange where there's orange, and then blue where there's blue all the way around. That looks pretty good. Now, if I add in another neuron and then I rerun that with 80% training data, and then we'll see, does this give us some extra to work with? It may not. We'll see. We'll see what it does. But it's looking pretty good so far. And you can certainly play with this for many iterations. And I got to tell you, that looks really pretty good. So I'm pretty happy with that. I mean, I've got a nice clean line for orange all the way around. I mean, look at that. That looks great. And then I've got a nice clear blue all the way around. And this is by far the best one that we've seen so far. Nice and clean all the way around. I'm going to go ahead and stop this. So this is a neural network. So this is exactly what a neural network does. I could add more hidden layers to this, but it's not necessarily. We can go to town. Why not? We'll just add in a bunch of neural networks. You can actually have in more. You can play with different architectures. You can come in here and see if this gives you something different or a more defined line. Adding more doesn't always mean it's going to make it better. You can see here, we'll let it run while I'm talking through this. I've added this kind of weird architecture to this neural network, and it's already not performing that well. So adding more doesn't always make it better. It's not terrible. I've got a line here. I got a nice little, but it's, I mean, it's not bad, but I got this weird thing that's happening here. So it's not as good as our smaller one. Even if I add in more here, let's see what that does. If I add more in and rerun this, is this going to give us a better, this one doesn't look too bad. Maybe it's kind of starting off in a good way. This looks pretty good. It's got promise. It's got this little bridge here on the blues that is a problem. So it's still thinking about it. We'll let it do its thing. It might resolve that bridge. But the good news is, no, it never resolved that bridge. It maintained that. So we got a little bit of crossover, although this looks pretty good, except for that. I mean, if I go to town on our middle neurons and then back off the side neurons a little bit and then rerun this, I mean, this is kind of, this is a large part of what humans are involved in, or we're still required to be involved in massaging neural networks, especially large language models as well, because there needs to be a farming process as it relates to humans are still really good at instantiating, enforcing pattern recognition, and then doing testing and evaluating. And this is a perfect example where more is not better. So I'm going to go all out, and I'm just going to add in a huge neural network all in. And where I'm going is we're running through a process of optimization, and it's not just a matter of throwing more at it to see if more is going to work. In this case, we want to find the optimal amount of compute to algorithmic usage. In other words, an efficient usage of the neural network. And in this case, a smaller neuron, this one actually worked really well. I'm throwing everything at it, and that is awesome. Now, this looks amazing, right? This looks really good. And this required us to create 5 hidden layers and 2. So we've got 5 times 7, 35 neurons, right, to make this pattern. When we were able to do something earlier, and this is a really good pattern, but we were able to do something earlier with a lot less, where we had 3 hidden layers, 7 plus 5, 12 plus 3 with 15 neurons. So we were able to do something quite a bit with quite a bit less, and be able to do something that was still the same. Now, I will say this is pretty good. This looks really good. And I don't have a lot of test loss, and I don't have a lot of training loss, so this is probably one of the best. But is it really the most optimal considering what we're trying to do? Probably not. Who knows? We can always add in another hidden layer and then see how it operates, and we can goof around with seeing what it does. Okay. While that's doing that, I think TensorFlow goes to up to a max of 6. I'm sorry, not TensorFlow, but this application does a max of up to 6 hidden layers, and so this is pretty cool. This is actually looking pretty good, although I do have a crossover little bridge between the two, so there's a misclassification here. I might resolve it by the time we get through. It's still working through it here. Okay. That is neural networks. That's deep learning in a nutshell. If you have any questions, again, text me, email me. But this wraps up all of our labs. My final learning activity is going to be just a lecture. It's going to be an applications lecture. I'll be on the lookout for that later this week. And it just totally flamed out here. That didn't work. So adding more made this actually worse after so many points in time here. So, okay. So what I'm gonna say is this wraps up our big technical labs. It's been a pleasure, going through this process with everyone. But I'll say that we'll get to the lecture after the last lecture for applied machine learning and applications in machine learning as it relates to everything you've learned up to this point. We're going to jump into a time given to you for your final quiz. And so the week 8 will be dedicated to best used by you as a student to study and brush up so that you can take your final, do well on your final quiz. Okay, with that, that's all I've got. I appreciate it, and then I will see you in the next and last learning activity 16.